Hello everyone, and welcome to the second part of week number 80, and today we are going to look at the Raku solutions of task number 2, which is called Count Candies. Let's look at the task first. So count candies. You are given rankings of n candidates. Write a script to find out the total candies needed for all candidates. You're asked to follow the rules below. The rule number A, you must given at least one candy to each candidate. Candidate with higher ranking get more candies than their immediate neighbors on either side. Right, so actually it's a bit tricky, but it's simple. So let me show you this on the second example. It's so there are different numbers unlike the first example. So there are rankings 1, 4, 3 and 2. So each candidate gets at least one candy. So yeah, that's for sure. So this one gets one, this one gets one, this one and this one gets one. All those people get at least one candy. But after that, we're looking at the person at position 1 with the first ranking 1, and see its neighbor has bigger score. So yeah, you will not give more candies to this candidate, right? The same happens here on this end. So well, yeah, there's only one neighbor for this candidate, for the last candidate in the list, and so it has smaller. This candidate has smaller score than its neighbor, so we'll not add any candies. So even if the first candidate has a score of 1 and the last candidate has the score of 2, they both get only one candy. That's the point. That's the crucial point. Because you kind of cheat and you want to minimize the number of candies. So yeah, this candidate only sees his neighbor or her neighbor, and that's it. So we do not care that this one has lower score. So basically this one should get one candy, this one should get 2 candies because it should get more candies than its neighbor with a lower score, but it should get less candies with the neighbor with a higher score. So it means basically that this candidate gets 3 candies, and it's still more than 1 candy here. So in total you've got, if you count correctly, it should be 7. Right, so yeah, that's kind of clear, but it's not straightforward. And let me start with my solution, because I will show you how I approach the task, and actually it's not an ideal solution. So here is my solution. So what I did, so first of all, I just call this Candies functions a few times, and I use the test module just to see the result, because with lots of numbers it's difficult to see whether the result is correct or not. And I also use some other cases, more difficult cases, less straightforward, because so here, like, all the rankings are just 1, 2, 3, 4, right? But what if we miss some marks, or what if like there are same marks in different places, like these 5 here and these 4 here, they both get the same number of candies, if I am correct. But okay, so nevertheless, so the algorithm is kind of a bubble sort in that sense that it loops over the solution a few times, and after you see that there's no change after the last iteration, you stop it. So you agree that all the candies are spread correctly, and you print the result. Right, so what I do first, I fill the candies array with ones, with units, and then I repeat this procedure. So I count the sum, and I see, and I look at the candidates and their neighbors and increment their candy number. If this candidate has a bigger ranking than its neighbor, and if this candidate did not receive more candies, because if the ranking is higher, then the number of candies should be bigger. So if that's not the case, I increment this. I did the same. So here's the line for the first candidate. Here's the line, actually exactly the same line, well, with some exception. Here's the line for the last candidate. So we see, so we're using these whatever constructions with -1 or -2, and here's the loop. Basically it does exactly the same, but for the candidates in between, which have 2 neighbors, right? So I do 2 increments for both. Actually, yeah. So that's I couldn't call this. I couldn't call this like an ideal solution, but nevertheless it works. And actually, what's interesting, I never saw. So you see, so there's say candidates for all these cases. There are not more than 2 runs required to get the stable result. So let me run this ash Raku 2, and voila. So you see, so first run, second run, actually third run. So, but on the third run, actually on the second run, I don't know why we didn't stop earlier, but nevertheless, so yeah, see, so after this second run, okay, yeah, I know why we didn't stop, because yeah, here we had some change. You see, so here this second position was incremented, and after that there's no change, so we stopped. And here we got the correct result just immediately, but still we needed the second run to confirm we didn't make any changes on that second run. So that's the solution. Okay, so let me go next. The second solution here in this list is the solution by Jan Krnavek, and here it is again. So we are using, Jan is using the test module, and there are some test cases, also some tests that are not listed in the task description, including some weird cases with letters. Basically, why not? Because yeah, if we're just comparing items, yeah, we can compare letters as well. And I see there are like really big difference in rankings, and also a negative ranking. Right, so we need to look at the function called count Candies, and there's the second multi-version of this main function, which just accepts some input from the command line. Right, so count Candies is the main function, so it starts here. It accepts the Slurpee array. Then you see, so dead CMP. Wow, that's an interesting thing. So I see there's no space between Z and compare, but actually it's basically we've got 2 arrays on the left and on the right side of those, and we zip them and we apply the compare operation. And compare is the smart compare operation, so it sees if it's a string, it will apply the string comparison operator. If it's a number, if there are numbers on both sides, numeric comparing operator will be applied. Right, okay, so we've got this. Then for all the keys in this array, but basically if you are talking about the keys of an array, it means that you're talking about the indices of that array. For all those, so you've got some indices, and if there are some, you apply the map function. Basically for all the keys you do something which with the instructions in this block. After that you increment. Basically I believe this is where we add the initial candy to each candidate, and then you just add these numbers up and get the results. So okay, so that's the thing. So for all the indices, right, what you do, so $_ is, I believe this is the index. So for everything on the left and everything on the right, from that position you determine the maximum. And remember that maximum is actually the binary operator, so it can be written not as a function max parenthesis a comma b, but you can just type a max b and you will get the same result. So this is what we see here. So we determine the maximum of these 2, so the part on the left and the part on the right, and for all those basically we take the slice, right, the slice of those of the results of comparison of each with each, right? No, with their neighbors, I believe, right? Because this is this is the original array, and this is the slice starting with the first position, right? So we just apply the same array, like shifted by 1 to the same array, and we compare the results. After that we call this count while function. You see there's the method operation operator, so you can call a function, this is a function, but you can apply it as a method if you will use the syntax dot and ampersand. So okay, so you count while so there's okay, so there's boolean flag, and it's defined, it's set here and it's not set here, And before that, we have basically some reference to the function, so it's kind of an anonymous. Yeah, we pass a lambda, whatever block, if to be correct. And this whatever block is checking the equivalency of this something with the less. So there are like more or less, and what's the equal? The third one with this thing. And yeah, actually maybe we have to take a look at this. It's like the fields of the order. Oops, too much of the order class. You see, so enumeration. So order, there is less, same, it's called same, and more. So there are 3 values, and you can use names, and even you don't need to mention the name of the enumeration. So yeah, you can do it like this. So you compare this, because do you remember that these stars will be using the values from from this slice, and this slice is already the result of comparison. So yeah, it will be less, more, or same. And right, and this this at n is basically this one, right? Because we're calling this as a method, and it this operator will pass the first argument as the first argument. Yeah, the invocant is the first argument. So if this n, then we scan it from the from end. So yeah, basically we are somewhere in the middle, and we look left and we look right, and we want to look to the left, starting from the closest position, right? And the same on the right side, but on the right side we just increment the indices, and on the left side, to look at the closest position, we should decrement these indexes. And then we map using this function. If it is if it is false, then we break it, right? And after that we return the number of such elements. I don't quite understand what happens there, but nevertheless I believe it will work. Raku 1 bash Raku chair 2, and we're using the default things. Why? Because test. So all these things work, right? So we don't know the sum, but it should be like 5 here, and actually, why is it 2 candies? Because this candidate should get 2 candies, if I'm correct. Let me Perl. Why is it still Perl? Weekly challenge, and challenge is number 80. Count candies. The output is 4. 1. Okay, so 4. Wait, then I solved it incorrectly, or because I give 2 candies to this one. Applying rule A, each candidate gets 1 candy. The total is 3 so far, right? Now applying rule B, the first candidate does not get any more candy at its rank, as its rank is lower than its neighbors. The second candidate gets 1 candy, 1 additional candy, as its ranking is higher than its neighbor than 1, right? Finally, the third candidate does not get any extra candy, as its ranking is not higher than neighbor. Okay, so I see. So yeah, I understood it incorrectly. So actually, if that's unfair. So, but why not this? Yeah. Okay. Let's remember that. So that's the correct result. So okay, the total number is 4, and here should be 7. 1, 2, 3 is 6, and 1 extra is 7. That's right. Okay, good. Going next, and the next solution here is the solution by Mark Anderson. Let us look at this solution. Okay, right. With help from, let's look at this. What's there inside?
Hello guys, welcome back to TechDose, and in this video we will see the Candy distribution problem.
Okay, that's the solution. We don't want to see it now. Right, so there's this unit sub blah blah function, alright? So it accepts the integers. Yeah, and actually with this syntax, everything here is the body of the main function. So it's a separate syntax for that. Okay. So we take left to right, I believe, something, and right to left, right? So we take the same array twice, and first we scan left to right, and then we scan the same array right to left. I believe so, yeah. And after that, we zip those. Again, yeah, we correct the direction here by calling the reverse for the second time. I would call it here, but yeah, it's the same. And then we find the maximum of those. So yeah, so we look at the array from one side, from one end, and then from the second end, and after that we determine the maximum number of candies for each, right? Right, so okay, so the candies function, so yeah, okay, so here we fill it with ones, then we skip. What do we skip here? I believe skip should get some argument. Is there any default argument? Oh wow, I didn't know that skip has a default value of 1. So yeah, we skip the first index, right? And we start, yeah, we don't want the first index because we make this -1 here, subtraction here, and if the current score is bigger than the score on the left, we increment the candies, right? No, we do not increment. We assign to the current position the score just a bit bigger than the score on the left, right? And we repeat this for all the rest. And actually, we do that from the right side here, and we look at the right side. So basically, k-1 means the neighbor on the right, and we return that. Okay. Then let's run this, and I want something. I want these, right? 1, 2, 2, Raku. So here's the solution we are working with. Mark Anderson Raku 2, and no, it will not understand that. And we want 1, 4, 3, 2, 1, 4, 3, 2. The result is 7, and 1, 2, 2. The result is 4. Okay, that's correct. Good. Okay, Mark Anderson. So the next solution here is a solution by Markus Holzer. So what we see here in this solution is the unit submain. So the whole body is the main function. We accept all the integers from the command line, and after that, so in numeric context, true is 1 and false is 0. Okay, we will use it in this sum. What I want to take a look at, to point to attract the attention is that the save method is not, the save function does not receive this, it receives this, right? So there are no parentheses, but this space actually allows us to pass this whole construction as a single argument, right? Basically, it's a number. Okay, so this number consists of some sum and the number of elements in the original data, basically. So this is where we introduce the unconditional candy for every participant. And here, what we do here, so we create the new array with some fake neighbors on the left and the right side, so that we have at least, well, so we have always we have 2 neighbors for each of the candidates inside this array, right? So, and this flattening is needed so that we just make it a whole construction with some numbers in it, or infinities. Right, then we take the sequences of 3 elements, right? So including those 2 neighbors, and we scan this whole array with those the window of 3, and we map those 3 too. So when we are inside the map, when we are executing this block, we've got the $_ the topic variable, and we can subscript this with these constructions starting with the dot. So it's basically there are 3 values: 0 the central element, and 1 and 2 0 the left neighbor, 1 is the central element, the current position, and 2 is the right neighbor, right? It can be by the way the infinity. What we do, so we sleep those, and actually these are, you see, so there are comparisons, and so we check if the current element is bigger than the element on the left, and here we check if the current element is bigger than the neighbor on the right. After that we just make the whole, well, the basically the flat array, and we add those up, and this is why we have this comment. So this is either true or false, but we are going to add them up. So we either will increment this by 1 or by 2 or by nothing, right? And append this. Okay, let's run the solution. Raku, Markus Holzer, Raku chat 2. We need some input 2, 3. What was that? 4, 3, and 2, and 2, 3, 4. That's incorrect, right? Okay, so yeah, I'm recording this particular part after I recorded everything. So there was some problem with video recording, but nevertheless, so you will see why this is incorrect later in the next part of the video. Okay, going next. The next solution here in this block is Simon Proctor, Raku 2. And so we receive all these things, which should be ints, and the maximum is basically the tallest, the biggest string, +1, and we append, we add up these things, right? What these things are, they are, again, so again, as in the previous solution, we prepend and append this max value. So instead of infinity, we just append the maximum values, +1, to the right and to the left side. Then we take sequences of 3, and basically we do kind of exactly the same, but just with different notation. So we have 3 variables here introduced in the signature of this pointer block, and all the rest is the same. Well, not the same, because we add this unconditional candy here in the middle, right? So we still count this, and not necessarily it should be in the middle, it should be in any place, because the order of these is not important here. So so central element on the left, central element, and its right neighbor. So, and actually for the elements, for the original edge elements, these checks, like for example this check, will always give you false, because this R is the last element, and this last element is max, which is bigger than any potential element here in the original position. This is always 0. Okay, so let's run this. Raku, Simon Proctor, Raku chat 2, 1, 2, and 2, 1, 4, 3, 2, and finally 1, 2, 3, 4. Right. Okay. Now we will continue with the next part with Perl and Raku solutions. Moving on to the next solution. The next solution is Arne Sommer, Raku 2. Okay, so here we have the main function. The whole file is the main function, which takes some numbers, which are all integers, and there should be at least one of them. We fill the Candies array with ones, then we append and prepend it with infinity, and Candies with zeros, right? So those fake Candies, fake people do not get any Candies at the moment, right? Hash m, which is, okay, let's look maybe at the output. So we output, what do we print? Well, okay, so we print the number of candies in the @c array. So this is, this is our candies array. Okay, so hash m, what is it? So for all the things, for all the items in the original data, but we modified this, right? So we have to fake people. Right, so we do that. So we put into this m, the hash is the index, and n is the score, right? The current score. Then we, so keys are the indices. So we saw those indices by the value, right? Right, this is the index. and what we do, we count the candies at the current position, and obviously we do it only once, right? So how do we count candies? So if we are at the beginning or at the end of the array, it is 0. Otherwise we return 1, but in between we can return the maximum of those values, which are so this is the maximum. Okay, so this line works only if the current position, if the value of the current position is bigger than the value of the previous position, or if the value of the current position is bigger than the value of the next position. So basically, yeah, so if the current position is higher, at least higher than at least one neighbor, then we take the maximum of those neighbors and we return that. And that's already the value that we wanted to do. And yeah, because we this at C, okay, so yeah, so we start, okay, so yeah, because I thought we will count the number somewhere from this hash, but actually, yeah, indeed, I saw this already. We count the number of candies in the at C array, where we keep the number of candies for each person, but we do not scan this array from left to right or from right to left. We just scan it starting from the highest scores, right? So the first is processed the highest, actually, yeah, the highest, right? No, actually the lowest, right? Because this is just the scanning and sorting, and we loop over those values. So we start with those positions with lower scores. Okay, very interesting. I like this approach. Maybe then we can run it. Raku, Arne, Raku 2, 1, 2, and 2. It should be 4, and 1, 4, 4, 3, 2 gives us 7. Yeah, that's the correct answer. Okay, next solution, Athanasius, Raku number 2. Right, this is the task. We accept some numbers from the command line. Our rankings, we append, so we keep those rankings as the numerical value from the command line. Okay, then candies, yeah, okay, so we fill it with ones. Nil, while, nil while. What does that mean? Is it just a loop with an empty body? So while this returns true, we do no operation, right? So okay, so distribute candies. Okay, if check rule B satisfies B, the solution breaks rule B. What is rule B? The rule B, yeah, this candidate with high ranking gets more candies than their immediate candidate with high ranking gets more candies than their immediate neighbor on either side, right? Wait, candidate with high ranking gets more candidates than their so yeah, okay, right, so it's nothing told about the candidate with the same ranking, right, as its neighbor. Okay, so we have to look first at the distribute candies function. It is here, so it takes the array of rankings and the candy distribution. Yeah, basically it's an array. Right, so okay, changed. I kind of already understand, and return changed. Right, so yeah, this because we are in a loop. So in a loop we will do something with those, right? And you see, so here we pass arrays, and here we accept them as scalars. So 4. You distribute left, right, left, right. So we scan the thing from the left side and from the right side. And what do we do? So we have two indices, I and j, and yeah, if basically, okay, this is what I had in my solution, right? So if the score is bigger but candies are fewer, then we increment it, and we report that we changed something, and the same but in the opposite direction, right? So we report the change, and if yeah, okay, so here in this procedure, this subroutine, what we will have after the call, we'll have the changed at C, well, $C, right, array. Okay, so yeah, so this stays unchanged, but this will be filled with the proper number of candies. And if we want to, so this is true by default, right? If we want to satisfy the second condition, what we have to do, we have satisfy B, or the solution breaks rule B. Okay, so we basically just make a check, so yeah, the question is if this function only checks the correctness, or if it also will fix in the same manner as we do it here. Right, so here's the solution satisfies B, the function. So we scan it again from both ends, right? And right, we only check if all the things all the cases. Okay, so yeah, we kind of confirm, because yeah, there's no direct information here in these algorithms whether we fill it or not, because we just okay, so yeah, in my solution I scan it and I finally test if there's no changes after the current loop. But here it's just we go from left to right and from right to left, and after that we expect that we found the solution, and here basically we make sure that the solution is correct. Okay, right, so Raku, Athanasius, Raku, 2, 1, 2, 2 should be 4. This is 4 in the number of candies. That's very good. That way you can see that, and 4, 3, 2. That's the number of candies needed is 7. And for example, if like this is really big, the number of candies should not be changed, right? Should not be different. And it is not different. The next solution is by Colin Crain, Raku number 2. Yeah, there's some rephrasing for dramatic effect. Right, so what we do here, we accept some data and we have this default list. We normalize that. And yeah, basically normalize. Yeah, the thing is, I really recommend you to go to this blog and read about the solution. So yeah, you have to navigate to the second part, and yeah, there's a really good explanation of how the solution is implemented. What's the idea behind the solution? Basically, the idea is you just try to approach. So basically, you try to cut all the tall piles of rankings, so that basically the difference is as small as possible, and in the end you will get the number of candies. All right, so this is called normalize. This is what I do usually: print debug information without any indentation, and then forget to remove this. Right, so there's input, there's output. There are two arrays, and what we do, so we sort the indices, or the indices by value. Yeah, we saw that in the previous solution. After that, using that order, so basically we start with the smallest, right? With the lowest position. Minimum we delta. That's cool. That's really cool. So we look one position left, one position right. Actually, right and left. And so this is a topic. This $_. And if this is ignore out of bounds, okay, then we continue. And if this is bigger than the neighbor, then minimum, what's the original? The original value is 1. The minimum gets the value of this. So basically it's the next, either the current minimum or the current height plus 1. So the variable is called min, but this is max, just above max or smaller values. Right, and after that we assign this min max min to the current cell, and that's it. So we start with the output, and this output is empty, and we will just loop over the elements only once, and we will immediately know after the first iteration the value at this current position, right? So once again, so we start with the smallest, right? And if we see if this one is higher, not this one, but if the neighbor, this is neighbor, the selected thing is a neighbor, either left or right, depending on the value of delta. If the neighbor is higher, then we assign to this current position this value. Okay. Either if the current, no, wait, this is the current and this is the neighbor. No, sorry, this is not the neighbor. This is the neighbor. This is the neighbor, right? So if current is higher than the neighbor, then we assign to the current the maximum. Either it's the previous maximum, which is called minimum, or it's the neighbor plus 1. So yeah, and because we start with the smallest, basically we just, right, so we just build the blocks from bottom, not like as I mentioned before that we reduce the values, but basically we build the values, but we scan. Yeah, so yeah, the main idea here is that we start with the smallest value. That's an explanation. If the given index value is larger than either of the neighbors, then it is valued in the output be the larger of its smaller neighbor's output plus 1. If it is smaller, then both it is 1. Okay, yeah. Okay, interesting. Raku, Colin, Raku, 2. Yeah, well, there's something. Right. There's no number, right? There's like say output, but it should be. We don't know the total number of counts, right? Of candies. And finally, 4, 3, 2. There should be 7. 1, 2, 3, and 1 is 7. So yeah, the result is correct. And this is obviously, what is that? 0, 3, 2, 1. It's, I believe, this is the order, right? So we start here from left to right. Yeah, there's no difference. But here we start 1, 2, 3, 4. Okay, interesting. The next solution, Jaldhar Vyas. We start with filling the Candies arrays with 1s as usual. At n is the input for all the elements. So this is an index. If the current element is bigger than the neighbor on the left, or so yeah, if basically I believe this is needed, this defined or when this neighbor is outside of the original data set, right? We increase the candies, and the same for the right neighbor. We increase the candies, and then we print the total number. Raku, Jaldhar Raku 2, 1, 2, 2 is 4, 1, 4, 3, 2 is 4. Yeah, notice by the way that this potentially can give different results, right? Yeah. Okay. Yeah, I wonder why there's no change. So here we have wait, we can call this with Colin Crain's solution, because there we have the distribution also printed, right? So the output is this, but it doesn't give you 7, right? So this is the number of candies that people should get would they have this distribution of rankings, and it's total, it's 10, not 7, right? Okay, yeah, but I believe we should have more test cases for the task, just yeah, on regular basis. Really different cases should be tested. Okay, that's next solution by Julio de Castro, and it's quite compact. So so this n.elms basically means that we give one candidate to each of the candidates. Here is, yeah, we saw it last time in the first task, that we need to convert those ints to integers to be able to use them properly somewhere else later. And this is the number of elements, right? So you see here you see actually two different forms of using the elms routines. Here this is a method, and here is just a function with no parameters, with no parentheses, but you don't need it because this is the whole thing, right? Okay, so here we scan. So this means that we have the range from 0 up to the element, the last element index -1, right? No, up, yeah, right. So this is the number of elements. This is the number of this is the index of the last element. Basically, you can just use .end instead of this, I believe, right? And this is up to, so not including some start from 0 and finish at the previous to last location, right? And we grab those indices. These are indices, so that the current value, the current index, is not succeeding. This is preceding. This is succeeding. Is not, and succeeding of the $_. $_ is the topic variable of this grep, and this grep loops over the indices. So this is the current index, this is the next index, and basically we count. So we count the number of cases where the current element is not equal to the next element. I don't understand why and how it should work, but we always can check it. 2 Raku 1, 2, and 2. This is 4, 1, 4, 3, 2. This is 7. That's correct, and this should be 10. Yeah. So yeah, I believe actually in my solution we like. Yeah, I don't have an input. Okay. Right. So that's. So yeah. Again. So yeah, we need more diverse test cases in the task, I believe. Okay, Kang-min Liu, Raku number 2. So we take the arguments, we convert them to integers from one line. The extra, so this is the extra, this is the, yeah, we know what that is. This is one candy for everyone. So we scan, okay, so here we have this end, but basically that's the same solution, right? But the only exception is that we check it to the previous neighbor, not to the succeeding neighbor, right? Raku, gug, Raku, 2, 1, 2, 2. This is 4, 1, 4, 3, 2. Yeah, it was said here, but this case 1, 2, 3, 4. Yeah, that's a difficult test case. Okay, we are going next to Laurent Rosenfeld, and his solution is here. Right, there are 3 test cases and 2 semicolons in the end. I don't quite understand why we need these. Just for diversity, right? It's the same, so no commas or commas. Okay, nevertheless, 2 spaces. Nevertheless, so we scan over those, and you see, so this is, yeah, because this array already contains other arrays, right? So we just keep it as an array, and we have this number of elements. That's right. I believe we will just append it somewhere. Yeah, this is already the count, so we set the count to the minimum. Yeah, okay, so indeed, so there are 2 approaches on at this particular moment. So we either can keep the array of candies, and for each cell we have the number there, which we have then to add up in the end, or we just can keep the total number, so we don't need the some additional data, some additional spaces for the additional array of candies. We scan the original data. Here is the index, and we increment the counter if basically the element. Which element? The loop variable is. Okay. Ooh, that's cool. So basically, yeah, there are like 2 postfix things. So there's postfix 4 and there's postfix if. If I am correct, this is the whole thing for if, and this is the body of that, and this is everything which will be executed for this for, right? So we loop over the left and right neighbors, and the $_ is basically this delta, right? So we check, and after that, if this neighbor exists, and if the value of the current position is bigger than the value of the neighbor for both of them, well, we check that for both of them, right? Well, it might happen then only one condition for one neighbor is true. Then we increment the counter, and we don't actually keep the number of candies, right? So we don't know how many candies each person receives. Raku, Laurent, Raku, 2, 1, 2, 2, 2. Okay, so yeah, we ignore these. Right, okay, but let me break this solution. Well, at least test this solution. So I want the case, I want this case 1, 2, 3, 4. That's the case I'm particularly concerned. Raku in T, ooh, like this, right? What? Help me. Okay, 2 spaces, probably that's why we needed those 2 semicolons. Okay, 1, 2, 2, 2, 2. Right, okay, so this is incorrect as well, right? Or maybe I'm not correct, but actually no, because this second person receives more candies than this one, so they should receive 2 candies. Then this one again receives more candies than this one, so the next one available value is 3, and this one gets more candies than this candidate, right? So it means that to this candidate we have to give 4 candies, and in total it's not 7, it's 10. Right. Mohammad Anwar. This is where we can test that strange case. Right, so there are some inputs, at least one of them, they're all positive ints. So you see, so there's a smart match against this subset, and the subset is a subset of integers where the value is bigger than 0. And basically, yeah, we just concatenate the result of this count candies procedure. And this subroutine takes the rankings where there's more than one, but basically I believe we don't have to repeat that, because all that, yeah, well, of course, definitely it's kind of different cases, but still, we just directly pass this. So in this program, probably it's a bit redundant, and we return the integer, and after that we concatenate that integer to the string, so it will be implicitly converted to a string. Left to right, right to left, so we append to both of them. Okay, so yeah, I believe we will find maximum, yeah, somewhere here. So we fill those with ones. Probably actually we don't need these, right? So we can just increment these as we saw in other solutions, because we're not interested in the number of candidates for each candidate, even so. So while this integer is within the range for this array, we increment, well, we set the number of candies bigger than the left neighbor if the left neighbor has lower ranking, and the same we do for the right neighbor, right? After that and what we do, okay, so yeah, so we're filling different arrays here, so left to right and right to left, depending on so yeah, here we decrement the counter, so we go from right to left, and we do that. And after that we find the maximum of those 2 approaches, of those 2 scans. I wonder if you could actually prove mathematically that this is enough, because you saw in Athanasius' solution there was a separate subroutine for checking this solution, right? So I wonder if you could mathematically prove that this solution gives you the result. Right, so for all those elements you just increment the count and return it. Okay, right, so let's run Raku Mohammed Raku Mohammed Raku 2 Raku 1 2 2. This is 4 1 4 3 2. This is 7, obviously. 3 4. Voila. This is 10. That's right. Okay, good. Okay. The next solution. The next solution here is Myoungjin Jeon Raku number 2. Here we see a few approaches, if I'm correct. Test with this subroutine. Right, so let's look at this one. So what we do, we just take the input thing. Where is the input thing, by the way? What is dollar underscore? Sorry, at underscore main. So here we've got the body. So yeah, this is the Polish way of accessing the parameters, I believe, right? It still works in Raku, but I believe I didn't use it for a long time in Raku. Okay, so you've got this, and you scan this. You take pairs, right? All possible the sequences of 2 elements, and you grab. That's an interesting thing. Yeah, there are too many brackets here, but the idea is that you see. So this dollar underscore is the list of 2 elements that you get from rota, and you compare them. So basically, all this means dollar underscore brackets 0 is not equal to dollar underscore first index, right, in square brackets. That's cute. I don't know if you even can remove this space, but nevertheless, and after that, so yeah, basically you count the number of elements which are not the same as the direct neighbors. Only one neighbor, by the way. Raku Jeon, Raku Ch2, 1 to 2, 1, 4, 3, 2 is 7, and yeah, maybe it's not quite fair that I understood that if I have to test this difficult case somewhere in the middle of this review. Probably the first solutions also suffer from the same problem, so yeah, excuse me for that. But nevertheless, so for the main solutions, for the main test cases, the solution gives the correct result. And these, I believe this is more or less the same, right? So there are some punctuation difference, and we go from okay, so here we, instead of using this, we just compare if it's less. Good. Okay. 2 solutions left. The next solution is by Roger Bell West. We have here a couple of tests, the default test cases, and what we do here. So we sort the list, this list obviously, yeah, so from, yeah, in scanned in order. But these are the indices, right? So yeah, okay, so yeah, we sort these. So we've got the indices sorted so that those indexes correspond to the increasing ranking positions. And after that, we'll loop over those indices, and number of candies, I believe, is 1. So if the current index is positive, can it be negative? And the left neighbor is lower than right neighbor, and this lower left neighbor exists, then we append. So yeah, we add to this number array the just slightly bigger number of candies, bigger by 1 comparing to the previous neighbor, and we do the same for basically we check the right neighbor right here up to the last element. And after that, we find the maximum of those. Okay, so how many elements these at and r can get? I believe it's 3, right? It's either 1 or this or that, right? And after that, we just add everything up. Raku, Roger Bell West, Raku Ch2 test cases are built in. This gives the correct result, but we don't know if it will give the correct result for some weird cases of the input sequences. Okay, the solution by Ulrich Rieke. So enter array and type E to end. We get these lengths. We get the number of candies. Yeah, obviously it's originally the lengths of the data, and we scan it from left to right. This is $I is an index, and if this index is within the borders, I believe, right? And if the neighbor is lower, then we increase the candy. And again, why do we need to check if it's bigger than 0? It's always bigger than 0, right? Because this is the condition here. So basically, this is unconditional, right? If I'm correct. No, wait. Sorry. Yeah. Okay. So definitely. Yeah. So we start with 0. So it will be not executed for the first iteration, and this will be not run for the last iteration, right? Yeah, because the last value that this $I can take is this len -1. Okay, so and for the rest, except the left element, we check if the current element is higher than the left neighbor, and we increment the counter. And again, we do not keep the number of candies for each candidate. Raku, Ulrich Rieke, Raku, Chat2, Raku. We need some input, but we will be asked 1, 2, 2, and run it again. 1, 4, 3, 2, and is 7, and finally 1, 2, 3, 4, and should be 10. Right. Okay, so that was it. So we covered like a dozen, a bit more solutions in the Raku programming language. About the task number 2, candy sharing of week number 80 of the weekly challenge. It's not Perl, please change it. And yeah, so yeah, success with Raku, and see you next time.